All right, let's get started. So if you have a quiz 13, please turn it in. I don't have your homeworks graded yet because I had research stuff that I had to attend to over the weekend. Hopefully I'll get it done by Wednesday.
Is it dead again?
Yeah, that projector was working this morning. All right, we're back to where we... Oh, hopefully. Yay, okay, great. So any questions since last time? Okay, so what did we start talking about yesterday? Not yesterday, oh my God. Friday, last time. It's already Monday, yeah.
We were converting PDAs to NFAs and vice versa, and we were...
Not to NFAs.
Or,
The other three-letter acronym.
CFG.
CFG, yeah.
Yeah.
So we were trying to establish that we can convert between a CFG and a PDA. So which direction did we actually show last time? Well, which direction did we convert from and to? Yeah, we did a CFG to PDA. So we did this direction. So that's done. So which direction have we not done yet? PDA to CFG. So that's going to be today and maybe Wednesday, because it's rather involved. So what was the first thing that we did after when we started to convert a PDA to a CFG? What did we do to the PDA first? Yeah.
We assumed one end state.
Yeah. So that was the thing that we did. So ensure the PDA has exactly one final state. Okay, cool. What else did we ensure about it? What else did we do with that final state? Yeah.
We can empty the stack.
We can empty the stack too. So we can empty the stack in this final state. So just to refresh your memory, if this is our PDA right here, the idea was we were going to make a brand new final state, and from all of the old final states, we have what I lovingly call a triple epsilon transition. If I can write small enough. That from all of the old final states, we triple epsilon our way to this brand new final state. So if we could accept in one of the original final states, we can now accept in the new one because we can just take the corresponding triple epsilon transition. So how did we tackle the can empty stack and final state thing? What did we do to that? Yeah, exactly. So we had a self loop on that final state. I'll actually make it a different color so we can see it. So self loop on that final state where we didn't read anything because we were supposed to accept in the first place. We can allow ourselves to pop if there's something there, and there's no reason to push anything because we're trying to empty the stack. So then we have a transition like this for all stack characters. So for every A in the stack alphabet, we just add one of these self loops on. So if the stack alphabet had A and B in it, we would have 2 transitions here. Okay, any questions about why this is? Or what we're actually doing here? Yeah.
Does the stack alphabet include the dollar sign?
So not necessarily. So the stack characters are just characters. We don't necessarily say this is a dollar sign which represents this. They're just any old character. So, but if it did, like in the constructions that we've done where we had the dollar sign, yes, we would include that. So every stack character has a transition like this. Yes. Any other questions? So, and by the way, you may be thinking, how in the world are we supposed to think about this? Like, how in the world did someone come up with this? And after the next step, we'll see why. But I defy you to be able to come up with this yourself. I wouldn't be able to come up with this. So whoever came up with this really had something in mind in order to actually convert the PDA to a CFG. There was a particular way this person must have been thinking. So there's actually one more thing that we're going to do before we start making the CFG. One more thing that we have to do to the PDA to get it quote unquote ready so that we can do the conversion. So the third step is to ensure every transition of the PDA so there are 2 possibilities. So it either pushes and doesn't pop, or does not push but does pop. And that's the third step that we have to do. So what we have to guarantee is that every single transition does exactly one of the 2 operations, push or pop. It can't pop and push, and it can't do neither of the 2. So it always does one of the 2 operations. So let's see. Well, what are the possible transitions in an arbitrary PDA? What could appear? So I claim that there are 4. So let's see. Let's observe these. Well, we could either do nothing, so no push, no pop. We could push, then pop. Oh, sorry, pop, then push. We could pop and no push, or we could no pop and push. So to illustrate what that looks like, let's say we have a transition of the form A epsilon to epsilon, or we could have it pops X and pushes Y, or we could have a X goes to empty, so it pops and doesn't push, or we could have a no pop and then it pushes Y. So every transition in a PDA looks like one of these 4. Okay? So which one of these are, someone's calling me. Which one of these transitions are okay with the third thing that we need to do?
The second one's on the right.
Mm-hmm. Yeah, so these ones are A-okay to me. Right? Because they do one of the 2 operations, so we don't have to touch those. But the other ones, of course, we have to do something with them. So how can we fix these transitions so that we obey this third thing that we have to do? What could we do? Yeah.
to get rid of like the epsilon and epsilon,
Mm-hmm.
could we possibly like push and then pop the same character just in a row?
Exactly. We could do exactly that. So what we could do is, as was suggested, transform this transition into two transitions. So on the first one, we just push some arbitrary character and we don't pop anything. Let's just say we push Y, but it doesn't have to be Y, or it could be anything. And on the second transition, we pop Y right after it. So we just make a completely new state. So I might as well notate that. So that's a new state. But what do we read on these transitions? Well, originally we had to read an A, yeah.
Oh, I was gonna say maybe an A at the beginning and then an epsilon for the next one.
Yeah, that's perfectly valid. So we could read an A on the first one and epsilon on the second one. You should note here that the A does not have to be a character. It could also be empty. But for our purposes of what we need to do for this third thing, it just doesn't matter. Because the third thing we have to do only involves the stack. It doesn't involve what we actually read. So we can do it like this. We could do epsilon on the first and then A on the second. It doesn't matter. Okay. What about the other one, the AXY one? Is there a way that we can fix that into, say, two transitions? Yeah.
You do in a similar fashion, read an A and then have X go to E.
Mm-hmm.
And then read an epsilon.
Mm-hmm. What should we pop on the second one? Because we've already popped.
Don't push anything and pop Y.
Not pop in this case.
Don't pop anything, push Y.
Right, yeah. So so we're trying to emulate the original transition, which says pop X, push Y. So because pop has to go first, we have to put the X1 on first. Okay? Any questions about that? Yeah.
Could A and epsilon, could we read epsilon and
Yeah, you could. So the reading order doesn't matter. The stack order does matter. So you have to pop first, then push on the second one. Whereas the first one, you have to push first and then pop because the stack could be empty. Okay, any other questions? Believe it or not, the PDA is ready to be converted to a CFG. And you may be thinking, how in the world is that sufficient? So I want to look at something that may seem a little unusual, but it'll actually demonstrate why we're doing this. So I'm going to make a plot right here. So on the horizontal axis, we have time. And on the vertical axis, we're going to have the stack height, or I guess the PDA stack height. Okay? So we're going to make a plot of what could happen here. Okay? So at the very beginning, what must be true of the stack height?
That must be 0.
Must be 0. So it must be down here. What must happen on the first transition? To the stack, I mean.
We add the dollar sign.
Not necessarily. But what happens to the stack height?
We can't pop anything because it's 0, we must push something.
Right, we must push something. Can there be a transition that pops or does neither of the two operations?
No, neither.
Nope,
Are designed.
because we got rid of them. So what happens is the stack height must go up on the first transition at least. What happens at the very end to the stack height? Well, when it goes to that one final state, it might not have an empty stack. But what do we allow it to do?
Empty itself.
To empty the stack. So we have a way for it to end with an empty stack. So way over here somewhere, it's going to come back down to earth at 0. But there's nothing in here that says, in terms of the PDA, there's nothing that says that it can't go back down to an empty stack at some point in the middle. It's not like it starts at 0, never comes back down to 0 until the very end. It could hit 0 multiple times along the way. So maybe the stack height looks something like this. Maybe it hits 0 here, has another mountain, hits 0 again maybe, and maybe it looks like this. Okay? So let's see. What are we going to do with this? Well, let's view this in a different way. So if let's just say the input string is W. So that's the string that we have read along this way. And what I'm going to do is I'm going to call this first part right here, I'm going to call that W1. The second part I'm going to call W2. And then the last bit I'm going to call W3. So we're not going to actually use these. It's just something that I want to demonstrate. So what could we, and let's just say that W is accepted by the PDA. What could we determine about W1, W2, W3 and their relation with W? So W1, W2, W3, those are the things that we have read in that portion. So W1's the string that we have read in that first mountain. W2 is the string we read in the second part. W3 is the string we read in the third part. So what can we say W is in relation to W1, 2, and 3? What's there? I could.
The length of W.
We don't necessarily know the length of W1, W2, W3 necessarily.
This is a wild guess, but is it W a deconstruction of W1, W2, W3?
Right, exactly. So W is equal to W1, W2, W3. Because the stack height is never 0. The stack height is never going to be flat after a transition. It either always goes up or always goes down. So if it hits 0 and then does another transition, it must go back up after that. So that tells us that if you read the string for one particular mountain across, that means that the entire string is just whatever you read in the first part, then whatever you read in the second part, etc. Okay? Does that make sense? So let's actually start making the CFG now. So here is how we make the CFG. And we're going to make a bunch of variables. So the variables here are A sub PQ, where P and Q are states of the PDA. Okay, so how are we supposed to interpret this? So the APQ variable, what I want that to represent at least is that variable will generate the set of all strings that go from state P to Q with the same stack height. Now, we haven't made the rules, so we'll have to encode this logic into the rules themselves, but that's what our goal is. So why do we want that? Well, think about it. Well, how many start states of this PDA do I have? How many start states? Just one. How many final states do we have? One. So what does the variable a sub q0 qf, where qf's the final state, what does that represent? That tells us all the strings that take us from q0 to the final state. But since there's only one final state, that's the strings that the PDA accepts. So that tells us that the start variable is a sub q0 qf, where qf is the final state of the PDA. Because that represents, or should represent, all of the strings that take us from the start state to the one and only final state. And because a grammar only has one entry point, one start variable, we have to encode it like this. So that's the reason why we made it so that there was only one final state. And, as we'll see in a second, why we wanted to empty the stack in that one final state. Okay? Any questions why that is the start variable? So how many of you have taken 302 or algorithms of some kind? How many of you do not know what dynamic programming is? Okay, so the basic idea behind the rules that we're going to make is we have this problem we want to solve, which is generating all the strings from Q0 to QF. That's what this variable represents. And if we can solve smaller subproblems and we can relate those smaller subproblems together, then we can achieve the whole problem. So like, if, for example, if we have tasks 1, 2, 3, 4, and 5, and each one of those has multiple instructions, if we can solve, let's just say 1 and 2, 3 and 4, and 5, and we know how to relate each of these groups together, then we can solve the whole thing. We just do step 1 and 2 first, and then do 3 and 4, and then do 5. So all we're doing is we're looking at a smaller subproblem and then relating all of the subproblems together. Does that make sense? Or do you want me to repeat that? Or give a different example? A different example, okay. So, let's see. So, this will actually be very apt for the example that we're doing. So suppose that we have to climb a mountain. Kind of looks familiar, right? So let's just say that we're down here. Or maybe not necessarily climb a mountain, but like, I guess that's fine. So what do we need to do? If we want to go all the way to the summit, what do we have to do? well, we got to start climbing up. And then what might happen, especially in this case, what might happen before we get to the summit?
We might hit a peak.
We might hit a peak, so we might go up here, so we might be there, but then what might happen? We're trying to get to the tallest summit. What happens in this example? Well, I got to go down a little bit, right? So then I got to come back up and then come back down a few times, and then eventually I'll get to the summit. So the basic idea is if we have to get from, say, this point right here to this point, well, we got to traverse each of the points in between. So let's just say, for example, that here's a midpoint right here, this little red point. And suppose that I know how to get to that point. And I know how to get from that midpoint all the way to the summit. So I know how to get to the midpoint, and I know how to get from the midpoint to the summit. So how do I get to the summit then?
Go from the midpoint up to the summit.
Yeah, so I know how to get to the midpoint, so I do that. Then I do from the midpoint to the summit. So it's just a smaller version, or not a smaller version. It's a sub-problem of what we need to do. We have a goal that we want to do, and we just do smaller versions of the same problem, and we just put them all together in a certain order. So that's what we're actually going to do here. So let's actually look at this in terms of what we have to do here. So let's look at a mountain that we need to observe. So let's just say that here's our, let's just say, for example, that there's one mountain in terms of the PDA's stat content height. So let's just say that we are at a particular summit right here. So let's actually expand that view. So what does it look like? Well, I failed art. So let's just say that here's a transition coming up. That's the summit, and here's it coming down. So, well, let's see. Well, if I'm at the summit, right there, I mean, do I know how to get to the summit? May seem like a silly question. At that point. So if I'm at that point, do I know how to get to that point? Yeah, because I'm there. Okay? So it may seem like a silly question, but how many of you have done induction? So what are the things that you need to do induction or solve a problem with induction? Base case and the inductive case. This turns out to be the base case. So if I'm all the way at the summit, well, what do I do? Well, let's see what happens. Suppose that I could be in any one of the states of the PDA at this point. So let's look at that. So what does that tell me? Well, at the summit, the transition that went up to the summit, the ending state that is right there, whatever state that I was in, is the beginning state of the downward transition. So wherever I ended up coming up the last transition is the same place that I'm starting at. So that's the base case of going from some state P to itself. Because it's where I started and also where I finished. For two transitions that occur right next to each other. Well, in doing so, what is the string that I generate going from the state to itself without doing any transitions?
Is it E?
Yes, the empty string. So we're going to generate this rule for all states P. Do you want me to explain that again? I know this is one of the harder derivations that we'll do.
Just to, what's P again?
So it's just an arbitrary state of the PDA.
Okay.
It doesn't have any meaning because we could be at a peak in any state. So this is just really telling us that if you're at a peak, you happen to be at a peak, then you allow yourself to be one by going to empty here. And we could, and if we can show that some state cannot possibly be a peak, then what we're doing here is we're just putting all possible rules of this form in, because I don't want to have to assume anything about the PDA here. All that we're doing is just letting any state possibly be a peak. We don't know necessarily which one it will be. But as we develop the other rules, it'll be clear which ones can be peaks and which ones can't. So, because they'll be enforced by the other rules in some sense. But does this one make sense, at least? It just means that we're at the peak. Okay, so let's do the next one. So this is the first type of rules. So I'm going to call this a type 1 rule. So if I have 10 states, then I'm going to make 10 rules. No problemo. So let's look at what would the next type of rule be. Well, it's the solving the smaller subproblem type idea we were talking about before, which is, suppose I have 2 mountains, and they touch down to earth down here, and let's just say here's another mountain. And let's say that I'm in state P way over here on the left, I'm in state Q on the right, and the state in the middle is state R. And of course, these don't have to be different states. They can be any set of 3 states, as we'll see. But this is just a possibility that could occur. So the goal here is always going from state P to state Q, always. P is the start of where I want to, from where I want to start. Q is my destination, and R is just some place in the middle with the same stack height. So let's see. Well, let's just say I suppose I know how to get from P to R, and I know how to get from R to Q. Well, what does suppose we know mean? Well, in the context of what we're doing, those are the variables. So remember, the variables say from some state to another state with the same stack height. So the P to R portion, that's going to be some string that A sub P R can generate. It's just some string that A P R can generate. And the second half is some string that A R sub Q can make. I don't know what those strings are, but I know that they can be, I'm supposing that they can be generated. So remember, the goal is from state P to state Q. Well, how do I get from state P to state Q if I know how to get to the state in the middle? Yeah, it's just the concatenation of the 2 variables. APR, then ARQ. And we're going to add a rule like this for all PQR as a state. They could all be the same state. They could all be different. Just every choice of 3 states. So the key thing to realize about this is, so I'm going to use a different color. So the P on the front has to match this one. The Q has to match here. And the two R's in the middle have to be the same. But other than that, it's fair game in terms of which is open season on which states these can be. They could all be the same, they could all be different, and we'll do an example of this. But the point is, the first one on the left has to be the first one of the first variable on the right. The second variable on the second state on the left has to be the second state of the second variable on the right. So they have to match up, but other than that, you can have any choice of three states. So I'm going to call this, as you might expect, a type 2 rule. Okay? Well, let's see. If we look at the two types of rules that we've made, so the ones that go to empty and these ones, did either set of these two rules look at the PDA's transitions at all? No, because the first one looks at all the states, and the second one, again, looks at states. So we need some that actually look at the transitions themselves. So here's how we're going to do this. So what we're going to do is we're going to look at two transitions. Well, at the bottom of the mountain, as we're going to start to climb up, well, we have to we have to push something onto the stack. And because the stack must end empty here, or at least can allow it to be empty, then at some point later, there must be a transition that comes down to 0 again. And let's assume that this is a singular mountain. So it doesn't hit 0 at some point in the middle. So what do we know about these two transitions then, if it doesn't come back down to 0 in the middle? What must be true of these two transitions? If it never comes back down to 0, yeah.
The first one's going to push something on the stack, and the second one's going to pop that same thing on the stack.
Exactly. That's the key here. So because it never hits 0, whatever we push on that first one is the thing that we're popping on the second one. Cool. Well, I don't know what states I'm in any of these, so I'm going to give them some names. So let's just say I'm in state P here. Let's just say the goal state is state Q, and the two intermediate states are R and S. So I could be reading anything on the first transition and reading anything on the second transition, but the things that involve the stack must be the same. Whatever we push on that first one, we have to pop it on the second one. So let's see. So let's just say, for example, we read an A on this one. It could be empty. We read a B on the second transition. Let's say for the first one, we push an X. It could be any symbol. And for the second one, we pop an X. It has to be the same symbol. Okay? So these are just two arbitrary transitions. As long as one pushes and one pops the same symbol, any pair of transitions is fair game. So as long as the stack operations match in terms of one pushes and the other one pops, then you can pick any pair of transitions. So let's see. Well, what is our goal? We're going from state P to state Q. Well, that's our goal. So we, of course, want to generate a PQ. Well, how do we get there? Remember, it's a singular mountain, supposing. So it looks to me like if I can solve the problem of going from R to S, could I solve the problem from going P to Q? Yeah, because they just involve two other transitions. So how do I get from state R to S? What does that involve?
That'd be ARS.
ARS. So we're assuming essentially by induction, we can get from that one state to the other one, and now we're just solving a bigger subproblem. So going from P to Q is the bigger boy that we need to work with, and ARS is the smaller one. So let's see, how do I get from P to Q? Well, one way is to do this, to go on this first transition, do whatever ARS can generate, and then go from S to Q. Well, what did I read going on that first transition?
A.
We read an A, good. Well, how can I notate any string that takes me from R to S with the same stack height?
Just that.
Just the variable, exactly. ARS. And then finally, what did we read coming down to state Q? We read a B. And that's it. So these are type 3 rules. So I'm going to say that this is going to be a rule for every pair. I'm going to be informal by saying every pair of matching transitions. And believe it or not, that's the whole thing. There's no type 4 rules. There's only 3 types of rules. So it's the ones that with the same state go to empty. Then we have the ones that go between 2 different mountains. And we have the ones that match up 2 different transitions together. Any questions about how it is? We're going to do an example, I promise. Although we don't have a lot of time, but might as well do an example. Okay, so let's do an example. So let's actually do the 0 to the n, 1 to the n example that we did last time. So I'm just going to faithfully recreate that PDA, hopefully without a mistake. 0, epsilon 0. Then we have the triple epsilon, Q2. Then we have the 1 transition. Cool. I think that's right. Hopefully I didn't make a mistake. So is this PDA ready to be converted into a CFG? No. So what are the things that are missing? Yeah.
For one, the middle step between the zeros and ones is like an empty.
Yeah. So this transition is clearly in violation. So what did we do to emulate this transition?
Just an arbitrary pop in the, or push in the pop.
Yeah, an arbitrary push in the pop. So I'm going to delete this transition right here. Switch to a new color. So I'm going to call it Q3. And we're going to have a transition. So the original one didn't read anything, so neither of these is going to read. But so here, let's push a $sign because we want to be rich. And then let's pop the $sign off in the same way. Okay. What else? Is there anything else that's wrong? I claim there is. So what else is wrong with this PDA? Something to do with that final state, yeah.
It needs to be able to empty itself.
Yeah, be able to empty the stack. We could actually prove in this example that the stack has to be empty if you go to that final state, but we want this conversion process to be completely algorithmic. So we don't want to have to think too hard about whether the stack will end empty, but it will in this case. So what do we do in this case? What do we do with that final state?
We're gonna have a self loop.
Yeah, a bunch of self loops. So which self loops in this case? Someone else. Yeah.
Get through all the ones.
Yeah, so well let's actually make sure. So what things are appearing on the stack?
We have a dollar sign, we have 1, and we have 0.
Does 1 appear on the stack?
Oh, no, sorry. Oh, just 0.
Just 0. So in fact, we can save ourselves a little work by, so we need to have a transition that pops the dollar sign off here, and we need one that pops a 0 off. So just as a quick assessment, let's look at the rules that we can make here. So let's see. So if I have, in the PDA that we made, we have 5 states. So how many type 1 rules are we going to make? Because there are 5 states. Yeah, 5. So that's not too bad. What about type 2? For every choice of 3 states. Well, how many choices for P do I have? How many choices for Q? How many choices for R? I have 5 each. So how many in total? Not 15. 125. Do you think we want to write out 125 rules? Hell no. Okay, so what we're going to do is we're just going to write a few rules of each. But could a program, could you write a program that just outputted all those rules? Yeah, certainly. Yeah, and type 3, well, we have P, Q, R, and S, so it could even be worse. So let's just write a few rules out of each. So let's just write 2 each, or maybe 1, because we don't have much time. So how many let's just do one example of a type 1 rule. So any example. Yeah. Yeah. AQ0, Q0 goes to epsilon. Good. So that's a perfectly valid example. Let's do an example of a type 2 rule. So remember that involves 3 states, yeah.
AQ0, AQ3, AQ1.
So the first one has to be...
AQ0.
Yeah, it has to be Q0, yep.
AQ1.
Q1, and then A sub...
Q1, Q3.
Good. Yeah, so the ends have to match, and the middle 2 have to also match. So that's a good example. So we're pretty much out of time. We'll do an example of a type 3 rule next time.